Okay, good afternoon, everybody. And today we're going to carry on our discussion about fire and explosion. We're going to conclude with this short discussion about explosions. There is also a movie for you to watch, so I'll try and keep the lecture part short. Just also want to remind you, please, that we have 1 week left to go. So 4 classes in total. All right, we finish next Monday. There is, I have not decided on a date for the exam. I just went to the exam calendar and I see that it's up to us to decide when to write that final test. So I'll probably set it somewhat later in the exam timetable. So it gives you time to revise fully. Okay, so let's think a little bit about what we've been talking about when we talked about fire. We talked about the oxidation of a fuel. So a fuel is carbon-rich source, which is burned together with oxygen to produce carbon dioxide, carbon monoxide, heat, and light. And also, and usually water as well. So in a fire, the rate of that oxidation is actually relatively slow. That is how we manage to control fire. And that's why fire is controllable. But an explosion is something entirely different. It is still an oxidation. It is still the oxidation of a fuel source, but the oxidation proceeds incredibly rapidly. It's orders of magnitude faster than occurs in an ordinary fire. And the result of that very rapid oxidation is the sudden production of large quantities of gas, carbon dioxide, water, vapor, etc., that is superheated and travels incredibly fast away from the point of the explosion. And the characteristic of explosions is this blast wave that emanates from the point of the explosion. Now, explosives themselves are then divided into different groups, and we talk about high explosives and low explosives. And again, what distinguishes them is the speed of the explosion. And whatever they are, whether they're high or low, we'll see the differences in a minute. The blast that emanates from the explosive travels incredibly fast, and you can picture it as a wind, really, although it's actually a pressure wave. But it travels up to 7,000 miles per hour. That is enough. That is fast enough that blast wave on its own can cause damage to property and definitely can cause damage to living things, which are relatively fragile. In addition, in explosives, in explosion situation, very often they are constructed in such a way that they shatter or break a container or materials contained in them, and that is itself flung out at high velocity and ends up causing damage as well. So let's have a look first at this group called the low explosives. Now, in the low explosives, the rate of oxidation is still much higher than it is in an ordinary fire. But the rate of oxidation in low explosives is relatively low compared to that of high explosives. And there are 2 low explosives which are very commonly encountered, and that is because they are used in firearms. These are the explosives which are placed into bullets. So in a bullet, the explosion of the powder does not shatter the bullet casing. The bullet casing is strong enough to withstand that. Instead, all of the energy goes to propelling the bullet itself out of and away from the source of the explosion. So this is black powder. This is still used, especially by people, hobby gun owners who like to make their own bullets and things like that. This is black powder, a very, very ancient substance, we believe first discovered thousands of years ago by the Chinese. And it consists of simple compounds which were readily available. And these are a substance called sodium or potassium nitrate, or saltpeter, it's called, charcoal, just ordinary wood charcoal, and sulfur. And charcoal, because it provides the carbon source for the explosion. The sodium potassium nitrate, and this in itself can be set alight, and it burns when it oxidizes. It actually releases oxygen. Now, this is a characteristic of most explosives, not all. I'll mention one where it's not. This is a characteristic of most explosives, is that they contain in them a substance which will release quantities of oxygen. And that oxygen feeds the oxidation. So they contain within them an oxygen source which will fund the oxidation. I'll give you an example quickly of one kind of explosion where this is not the case, where we've purely got a fuel. If we have large quantities of a carbon-rich fuel and abundant oxygen around it, and the fuel is in such a form that it can be easily oxidized, we can get that to explode. An example of this occurs in factories where material is made, linens and fabrics are made, cotton fabrics especially. They, during manufacture, they continually flake off some very small particles of cotton, which accumulates, for instance, in the eaves or in the roof. It accumulates as a lint. And if that lint is not very carefully vacuumed out or swept away, it becomes extremely explosive because it lies there in thick beds, rich in oxygen, rich in fuel, and it is highly flammable. And if that is set alight, it will in fact explode. It will oxidize so rapidly that it will act as an explosive. So there's an example where we have just an ordinary source of fuel, abundant oxygen, and we can get an explosion. These, however, these substances are unique because they contain this substance which itself is rich in nitrogen, in oxygen, and that is a nitrate. In many, many, many of the explosives that we use a nitrate of some sort because they do contain a lot of oxygen chemically bound into the substance, and once the explosion begins, then this oxygen is released and funds the future of the explosion. This is black powder, not used so much anymore and not used in modern ammunition. Instead, in modern ammunition, they use this. It's called smokeless powder, and it consists of a substance called nitroglycerin, nitrocellulose, and there's the nitro again there. The nitro part is rich in oxygen, it's a nitrate. And then the cellulose as we have produced by plants, etc., rich in carbon. And so there is a fuel source right there. And it's prepared in such a way that it is stable. And we're going to see that these have to actually be detonated in some form or other. They have to be set off. They don't just explode spontaneously. So these low explosives, the rate at which they oxidize is relatively slow. Now you can picture it in the following way. When we talk about these explosives, we're going to initiate oxidation at a particular point in the amount of explosive that we have, and that oxidation is going to spread rapidly through the whole substance at a certain rate. And in low explosives, that progression is relatively slow. It's much faster than a fire, but much slower than in high explosives, which we're going to talk about in a minute. The other characteristic of these low explosives is if we don't contain them, if you leave them in the open and light them, they simply burn. They don't explode. It's only when they are contained that they become explosive. And that's for various reasons. First of all, when they're contained like that, the speed at which the oxidation occurs increases markedly so that they actually behave like a higher explosive. But second of all, when they're contained, they produce the superheated volumes of gas, which rapidly expand, and they expand so rapidly and so powerfully that if it's constructed in such a way, the container can explode. In the case of a bullet, it doesn't. In the case of a bullet, the pressure is relieved by pushing out the bullet itself. So these low explosives are very commonly used. First of all, you can make them quite easily. You can make black powder quite easily. And they're very commonly used in homemade bombs, either for people's amusement or for malfeasance. And they can do a tremendous amount of damage. If you pack a lead pipe with sufficient black powder, for example, the resulting explosion can actually blow that lead pipe apart. And then the blast itself, in low explosives, the blast doesn't perpetrate for very far. But nonetheless, the blast itself could cause damage. But really, in those kind of bombs, it is the fragmenting of the container that really does the most damage. Now, then the next group of explosives are the high explosives. In the high explosives, thinking about this, the same process, right? We're going to initiate oxidation at some point in our amount of high explosive that we have. That oxidation front moves through the substance incredibly rapidly. It moves in low explosives. It moves through the substance. It can be measured in meters per second in a low explosive. In a high explosive, it proceeds through the entire substance at kilometers per second, orders of magnitude higher speed. When we ignite a low explosive like this, the explosive is almost literally burning. We refer to this in low explosives as deflagration. That's when a low explosive explodes. But in high explosives, with this very rapid oxidation of the entire substance, almost all at once, we call that a detonation. There is a difference. The detonation is much more rapid, much more violent, produces much more energy than a deflagration. So there, in the high explosives, there's also a division. And the first kind of high explosive to think about are the primary explosives. Primary explosives are extremely dangerous because they are so unstable. And they will explode in response, for example, to even slight increases in heat. They don't necessarily need to be lit. They will also very often explode in response to shock or to friction, quite apart from the fact that they can indeed be lit as well. So the one place where we'll commonly encounter primary explosives is as a detonator, is as a small, where they are used as a small explosion to set off a much bigger explosion in another kind of explosive. So for example, in a bullet, that little primer at the end of the bullet, cast your minds back And you'll remember if you look at a bullet, then there's a little circular, usually silver primer. That primer contains a primary explosive. As long as it's contained like that, it's safe. There's nothing going. But if you punch it, for example, as we do with the firing pin, that is sufficient to set off the primary explosive contained in it. And the primary explosion is enough to set off the smokeless powder or whatever it is that the bullet casing has been filled with. Primary explosives are very commonly used in this fashion as a detonator to set off an explosion in another explosive substance. The other thing about primary explosives is they tend, whether they're contained or not, if you set them off, they explode. Even if it's a very small amount, it will go off with a distinct bang, for the simple reason that it detonates so incredibly rapidly. All of that, the fuel substance is instantaneously almost oxidized. And even a very small amount will produce a distinctive blast wave, which we perceive as sound, for example. Secondary explosives are also high explosives, but the secondary explosives are much more stable. They're not entirely, but relatively insensitive to heat and shock friction. And this makes them much more useful to us because they can be handled so much more easily. And if you take a secondary explosive and light it in the open air, a small amount will burn. A larger amount of secondary explosive, however, will detonate. Even if it's not contained, a large amount will detonate and produce a significant blast, even if it is not enclosed within a metal container or something like that. However, the real useful property of secondary explosives is that they require a primary explosive in order to be detonated. This is what makes them useful, because they are relatively safe. We can work with them. We can do whatever we want with them. If we want to be blasting rock, we can drill a hole, pack the hole with the secondary explosive quite safely, and then put a primary explosive in which we detonate remotely or in some way. So the primary explosives, there are many, many, many of them. But one of the ones that you have probably heard of is nitroglycerin, and I've mentioned that already. Again, let's have a look. Glycerin is an organic substance rich in carbon, and the nitro part, that is the nitrate part that contains a lot of oxygen. Nitroglycerin is extremely explosive, very, very unstable substance. But you'll see now that it becomes modified in other explosives to be more useful and more handleable. There are many others, ammonium permanganate, for example, ammonium chlorate, benzoyl peroxide, and picric acid. These are all primary explosives. The secondary explosives are things that you definitely, many of them you will have heard of, because things like dynamite and TNT are secondary explosives. There's some that you may not have heard of, much more commonly now, a substance called penta-erythritol tetranitrate, which is a mouthful to say, so it's just called PETN. And then this cyclotrimethyl nitramine, I'm sorry. This incredibly long mouthful of a tongue twister. If you just look at different parts of it, you will realize trimethylene there, that is carbon rich. That is a carbon-rich substance. And there's this nitramine there. Just listen to the name, nitramine. It's rich in nitrogen, it's rich in oxygen as well. And that is providing the oxygen source. In all of these, there is this characteristic that they contain a substance which is both a fuel and an oxygen source as well. So the explosion funds itself with its own oxygen. Again, this very, very rapid detonation and this incredibly rapid production of a large volume, very large volume of superheated gas and steam and everything else produces a blast wave which rushes out and it is up to 7,000 miles an hour. And characteristically, in the high explosives, the amount of energy generated is enormous. So this blast wave can travel very, very far. And if you want a good recent example of this, just think about the explosion in Beirut Harbor. And if you've seen those incredible videos of that explosion in Beirut Harbor, you will you are able to visualize the blast wave as it moves out, because it creates a shell of water vapor, which appears as a spherical cloud as the blast wave moves out. And you realize that explosion in Beirut Harbor damaged buildings kilometers away. The blast wave was sufficiently powerful that it could travel that far and still be damaging kilometers from its source. These explosions contain a huge amount of energy, just an incomprehensible amount of energy. So the nitroglycerin is extremely explosive, unstable, primary explosive, but it can be stabilized. And this was what Alfred Nobel did, Alfred Nobel of the Nobel Prize. That's where he got all his money from. He invented this substance called dynamite, which we so commonly hear about. But dynamite is nothing more than nitroglycerin, but it is stabilized. It's mixed with inert substances. It's mixed. He initially mixed it with clay, with special clays and things like that. It remains explosive, and it is highly explosive. It is a high explosive, but it is completely stable, and it needs now, it loses its primary characteristic, which is it now needs to be detonated itself. It can't just be set off. It can't just be exploded all on its own. It needs to be detonated. He also, by the way, invented another substance which is somewhat similar, called gelignite, which you may also have heard of. The difference between them was the way in which they were stabilized. One was stabilized with things like clay, and that sort of. Gelignite is stabilized, is literally in a gel, and is stabilized that way. These dynamite, you can definitely still get it, but it has been supplanted. Instead, now most commercial blasting and that sort of thing is done with an ammonium nitrate based explosive. Now, this is really important because ammonium nitrate, there it is there. Again, here's our nitrate, here's our source of oxygen, explosive source of oxygen. But the ammonium nitrate based explosives consist of this, and then a fuel source of some sort. And this is where they become tremendously important in forensics, because it is possible to make this relatively easily. And huge bombs have been constructed out of ammonium nitrate and a fuel. Very often a fuel oil is used, and these are referred to as ammonium nitrate, fuel oil, and for bombs. And they also need to be detonated. They need to have a detonator attached to them to be set off, but they are extremely dangerous, extremely powerful. And one of the things which is so important about them is that this substance, ammonium nitrate, is exactly the same substance that farmers use on their fields to fertilize crops. Ammonium nitrate is a common fertilizer, but it can be used to construct an explosive. So all of these require detonation, and the detonator is usually a primary explosive, or some other, maybe sometimes they might even use black powder or something like that. But it's in this case here, these two here are electrical detonators. So they set off a small explosion, which will set off the secondary explosion. And these can be they have to be constructed with a substance, which can itself be detonated with an electrical current. So this would be a primary explosive probably. This is a detonator which is lit with a fuse. And these detonators can be something like black powder or something like that, but many other substances are also used in detonators. So this one lights the fuse, and this fuse can be several meters long, and they burn at a certain rate. The manufactures them to burn at a set rate, so that you know how long you've got before the explosion is set off. The electrical ones are really useful because they can be detonated from far away, because they just trail an electrical cord from the site of the explosion to where it's being set off. Okay, so here is one of the most important of all of the cases that, in the United States, which used ammonium nitrate as the basis for a bomb. There had been earlier in the 1970s, the initial attack on the World Trade Towers was also the same kind of bomb. This is the infamous Murrah building bombing, which was the responsibility of Timothy McVeigh. And this bomb was constructed out of ammonium nitrate and then fuel oil. So it was a typical ANFO bomb. But it points to the kind of problems that an explosives investigator faces when they arrive at the scene of a crime. First of all, the bomb is relatively easy to make. The substances, nowadays, a much more careful track is kept on ammonium nitrate. Even farmers who buy ammonium nitrate have to register and account for all of their ammonium nitrate that they use. But that was a relatively recent innovation. Before that, ammonium nitrate was relatively easy to buy clandestinely. It was not necessary to do it clandestinely because you could do it openly. Nobody kept any records. Timothy McVeigh and maybe others packed a truck full of ammonium nitrate and the fuel oil. And he actually set it off with a lit fuse. He simply lit a fuse in the truck, and it burned sufficiently that he was able to get several blocks away to another vehicle and leave the scene as the explosion went off. It was a catastrophic explosion. This was the Murrah building in Oklahoma City, and it tore almost half of the Murrah buildings right off the building and crushed it to pieces. And numerous people died as a result of this explosion. So you can imagine the priorities that this explosion investigation got. And here's the major problem. Look at that. How do you even begin to investigate a scene like this? Realizing that all of the parts of the weapon that has been used, which was the truck, have been shredded and have been blasted. There's some pieces kilometers away from the scene, and everything covered with debris from the results of the explosion. So the explosion, as it goes off, vaporizes much of the evidence that would lead you to be able to solve the crime. Nonetheless, the crime scene has to be as carefully investigated as possible. And they collect every single piece that might have belonged, for example, to the vehicle that was used. It is often quite obvious where the vehicle was, if it was driven up in a vehicle and that exploded, because the blast is sufficiently high that it will actually leave a crater behind. What they did, I thought I had a picture. Yes. I'm just going to flip forward a little bit. This is another view of the scene. They collected everything really, really carefully. And when they did so, here's the bomb crater at the Murrah building. It at least allows the investigators to locate the epicenter of the explosion, and they can then move out from that and try to find whatever they can. In this case, they were incredibly lucky because they found the axle of the truck, almost entire, the rear axle, and there on the axle was the vehicle identification number there, still perfectly preserved. And this was traced, and they found that this was a Ryder rental truck. They were able to identify the rental agency, and they were able to get details which linked Timothy McVeigh to the crime. He, in the meantime, had been arrested on entirely coincidentally by a traffic officer who found, I think, an outstanding arrest warrant or something like that. And then they managed to put the two together. And he was convicted and finally executed for this crime. But yeah, this is goes to the importance. This was found some distance away. I can't remember how far, but some distance away from the scene of the explosion. Okay, so there are numerous other explosives. RDX is one of them. You'll often hear it referred to. And RDX is important because it can also be made into a plastic form, which can be molded very easily. It still requires a primary explosive to set it off, but it is an extremely dangerous substance because it can be concealed very easily because it is malleable. Trinitrotoluene, again, just have a look at the name, and there, look what we have sitting right in the middle there. The toluene part, very rich in carbon. The nitro part, rich in oxygen. And here we have another of these substances, which has all the elements of an explosive substance because it has a fuel source and an oxygen source all in the same compound. And this is TNT, which you very frequently hear about. It used to be used very widely in weapons production. Nowadays, there are more modern explosives which they use to much the same effect. But TNT for many years was the explosive of choice in weapons manufacture. The criminals are continually on this search for easily manufactured explosives, especially terrorist organizations have developed numerous methods for creating high explosives just from basically what amount to household substances. Here is one, for example. This is triacetone, triperoxide, and it's abbreviated TATP. And this is made by combining acetone and peroxide and treating it in a certain way with acids and things. And it is a liquid, which is a high explosive. And this, I believe, was what the famous shoe bomber was using when he tried to blow up an aircraft. And it's this reason, this substance is the reason that we have to turn in all of our water bottles and everything. And you're not allowed to carry anything that is more than a certain volume. In fact, there are some of these things which they can put them together when they're on board the aircraft, go into the bathroom or whatever, and mix the substances and end up with an explosive. So, or this is the reason that they are so careful about allowing liquids onto aircraft. Okay, that's what we've done. So in many ways, the explosives investigator, is looking at many of the same problems that a fire investigator looks at, because so much of the evidence is destroyed. But the scene of the explosion can be analyzed, and also you need to realize that even though the explosion is so incredibly rapid and so violent, traces of explosives are very definitely left behind and can be analyzed in the laboratory if collection is done carefully. So the same kind of collection is done. Debris is collected, sometimes a very large amount of debris is collected and put into airtight containers, and of course labeled, entered into the chain of custody, and they can be analyzed then by gas chromatography or whatever to try and identify the actual fuel mixtures that were used. As much of the bomb as is left can be found and collected, is collected, and if need be, is put together again. Especially in serial bombing cases, the bomb maker adopts certain patterns of bomb making. It's almost like a handwriting that is written into the bomb itself. And a skillful investigator looking at the construction of a bomb can often be able to say, this is the work of so-and-so. This is the work of, such and such a bomber. We've seen these bombs elsewhere, etc., and put them together in a pattern. Even from small parts of the bomb may give clues as to how the bomb was constructed. One of the difficulties associated with an explosion is that some of the evidence may in fact be embedded because the force of the blast is so strong. Some of the evidence may actually be embedded in walls and in wood and everything. That must still be assayed. It must still be collected if at all possible. And the identification of the components of the bomb, as I've said, you can use gas chromatography, but there is another kind of technique called ion mobility spectrophotometry. Just remember the name. You don't need to worry over much about how it works, but just realize there are some very, very sensitive mechanisms whereby components, the chemical nature of the bomb can be assayed. Oh, here's a kind of explanation. It's working in the same kind of way as all of these things do. It actually converts sample to ions and then measures their mobility through the instrument. Okay, so that basically is a whole array of chemical tests that can be done. And the identification of the components of the bomb is important because they often point to a supply line. So the bomb maker had to obtain the explosive mixtures, for example, from somewhere. And often just the identification of the chemical nature will lead investigators to a particular manufacturer and then to a particular retail outlet. And there are not that many of them. So the chances are relatively good that some information at least will be gleaned by tracing a supply line and seeing if anybody stands out in anybody's memory or in records as to having bought material. Nowadays, for example, people frequently buy over the internet. They buy components over the internet. But even that leaves a solid traceable trail. So to finish off this section, I want you to watch this movie here. It's the FBI Files movie about the hunt for the Unabomber. The Unabomber was a typical serial bomber. He was extremely difficult to identify and catch. And it was really serendipity more than anything else that led to his eventual capture. He constructed bombs extremely slowly, and so they only appeared every now and again, and they seemed to appear at relatively random places. It became apparent that he had particular animus towards people working in computers and things like that. But he actually was eventually caught because his own family recognized characteristics in a manifesto which he published about his bombing. They thought they recognized certain things that he said. And he was investigated and found indeed to be the bomber. But this gives you a very good idea of the kind of forensic work that needs to be done in order to try and trace a bomber like this. Okay, and that is it. And I'll see you then on Wednesday.